All right, class. This week, gonna be pretty quick stuff because you have a lot going on in your project. But I want to talk about design patterns, and refactoring this week. The distinction this week is in so far in the class we've talked about, in addition to agile methods, but in terms of quality construction techniques, we have been focusing on things that help you with defect discovery. In a few places, I've talked about the concepts of defect discovery, defect injection, when defect is actually created, defect discovery, when you find it, and then there's remediation or fixing bugs, right? Excuse me. Um, but so far, unit testing, code reviews, static analysis, these are things to help you with defect discovery. And perhaps with even preventing defects, defect prevention, avoiding things being injected in the first place. But for the most part, in a traditional cycle, we may write our test after we write our code. We run our test, we find some defects. We do a code review of code we want to check in, or maybe it's on a user story branch and we want to pull it into master. So first we want to do a code review on it. We may discover some defects there, or we run static analysis on it and it gives us a whole bunch of output. And hey, we want to find out whether those things are really defects and then go ahead and fix them before we pull into master. Switching gears though this week, when we talk about design patterns and refactoring, these are actual construction techniques. In other words, things you actually change in the code to fix defects or just to improve the internal quality of your code. So from that perspective, this week is kind of special in that regard. We'll do some stuff for our last module that will include this as well. But let's talk about design patterns and refactoring from the perspective of actually improving our software, actually modifying code to make its internal quality better. So from that perspective, this talk is about design patterns. Now, design patterns is something that I believe everyone kind of had already talked about last year, so this is going to be a quick review, relatively quick. I know there's probably, you may have to go through this a couple times if it's something you didn't quite get in CST315 or something you're rusty on, but I'm presuming this is mostly review material, so I'm going to go through it relatively quickly. Oops, went too far. All right, so what are patterns? You probably heard this definition before. Patterns are reusable solutions in a context. Context may be defined as, when specifically do you use it, where do you do it, what are the trade-offs that could be based on lessons learned from things that you've done in the past. The context is important because even though it's a reusable solution, you have to understand not just the problem it's trying to solve, but the specific situation going on to know whether or not it is appropriate to apply the pattern. There are all kinds of these patterns. I mean, reusable solutions in a context is very generic, right? That's because patterns can be very generic. I believe, you talked about, when you talked about patterns in 315, you heard the story of Christopher Alexander's 1977 work on architecture and patterns, and that was done from an urban planning perspective, right? He was a PhD student in architecture, and was talking about patterns that you normally see in cities and so forth in urban environments. But then it translated and caught fire over here in software engineering. And the reason why is, you took a design course and you were talking and you're trying to use that modeling language to reason about software at a higher level, at a model level, not at the individual lines of code level. Right now, you're going through a significant software package where you're trying to understand what the structure is of it, what are the patterns of interaction, those consistent things you see over and over, and you kind of need to be able to identify that those higher order abstractions. All right. So modeling is one way we represent those abstractions. But even within those modeling elements, ways that things are commonly arranged provides an even higher order vocabulary around things so that you can talk about them. And I'll revisit that when I summarize this stuff at the end. But probably one of the principal contributions of patterns is being able to form this common vocabulary with whoever you're collaborating with. But again, there are different kinds of patterns: design patterns, analysis patterns, and process patterns. And other patterns on top of that. There's anti-patterns, patterns of things you don't want to do, or patterns of bad solutions. We are talking about it from a design pattern perspective. They've also been called coding idioms. These things, given that we are in software construction, I'm talking about the code level, those things that you can introduce or target refactorings to, which we'll talk about in the refactoring discussion. So ways that you can arrange those low-level classes and objects that you're writing and the behaviors on them to have a higher level of internal quality. Analysis patterns. Martin Fowler wrote the Analysis Patterns book, a really good book, particularly from a requirements engineering perspective. Kind of allows you to see not just patterns of solutions, but in a way, those are patterns of problems, ways to break down problems, common problems you see across different domains. So it kind of tries to articulate that. I've seen this before. In fact, in the pattern community, there was always this kind of acronym called the Quan. And again, I'm older than you probably, and so if you don't remember it, there was a popular movie called Jerry Maguire. In Jerry Maguire, the star wide receiver for the Cardinals talked about the Quan, right? This kind of psychic, mystic Zen like feeling of quiet that came over. The Quan in design patterns is quality without a name. Is what it refers to in the patterns community. So what it was is, when the patterns came out, the Gang of Four book came out. This is 93, 94. The first paper showed up. The book showed up. What it was really the authors were articulating things that master developers had seen over time, over and over, but were never able to place a name on it. Common ways of replicating their solutions in different contexts and doing it a particular way, but no one ever put a name on it. So the kind of the landmark contribution of the Gang of Four book, as it's called, which I've linked to off your Blackboard site, was to actually put a name on these higher order elements or arrangements, and thereby increasing the community's vocabulary. And since then, there's been, again, all kinds of things. The analysis patterns. Jim Copeland has process patterns for business process elements. Linda Rising did the Patterns Handbook. And in fact, there's a whole set of conferences for years, the PLOP conferences and workshops called the Pattern Languages of Programming, where folks have practiced writing new patterns and extending the set of patterns that we know in different domains. All right. So the key thing, patterns capturing domain experiences from master practitioners that solve real problems, real tools that you can use every day. So the challenge is kind of understanding, when and where you can apply these things, and that takes some practice. Patterns weren't taught to me when I was in college. They weren't even articulated then. They were kind of things that you learn over your code reviews over time and in the more code you wrote. Now we're trying to teach these things, in our university curriculum, and sometimes this can be a little bit difficult for students who are relatively new to coding, because you haven't quite found that you haven't written enough code to kind of intuitively see these patterns and the opportunities for presenting them. So it can be a little struggle at first, admittedly. As an aside, part of the reason that this has been such a really interesting research endeavor is, pattern matching and the ability of the human brain to be a pattern matching machine is something that across many areas of computer science, researchers are trying to get the computers to emulate. So, for example, chess. If I play chess. I don't know if you play chess, but you've probably heard about, Deep Blue playing Garry Kasparov and things like that, where the computer by brute force can explore so many configurations of a board. What happens with that is you have this state space of all the possible boards that you can have with different moves that a player makes, and it expands a whole big tree of stuff. All right, and the reason why that's interesting is the tree is so large in chess that the arrangements of a chessboard is more than stars in the sky, somebody once said. I forget that quote, but that's basically what somebody said, which means it's too big for the human mind to comprehend. We can't exhaustively explore and keep track in our memory all the different ways a chess game can turn out. All right. But a computer theoretically gets much closer than we can. Now, it's still computationally intractable. The computer can't do it all. But the massive computing power of a supercomputer gets a lot closer, so they can search way more of this overall state space than, say, the human brain can. Maybe the human brain can only do that much. All right. If that's the case, then how could the human brain ever beat a computer? Well, the point is the human brain is a much better pattern recognition machine. What they show in the human brain is that the human brain is able to quickly optimize very deep paths in the configuration of possible boards. And they hypothesize that happens because chess masters have played so many games that they can understand kind of, hey, I've seen this board. I'm right here. I've seen this board before, and these are the likely outcomes. And I'll skip all this other stuff as noise, right? I know that's not going to happen. The most likely outcomes are these. And it's very difficult to train a computer to do that, all right? Another area, let me try and erase my mess again. Right. Another area where pattern matching is very big in computer science is in machine learning, graphics, visualization. So effectively, so much of computer science now, and even software engineering, is in the area of data analytics. Right, going through massive amounts of data, and making conclusions. In the graphics visualization world, one area of work is simply to visualize structures, visualize things, because the human brain is such an effective pattern matching machine. And so the work of visualization are interesting ways to present data that are amenable, cognitive psychologists tell us, to human interpretation. We can understand them very quickly. All right, so ways to boil down massive amounts of information into a visual representation so the human mind can comprehend very complex scenarios. That's using the computer as a tool to enable the computer in your head, if you will. Machine learning and data mining is more about actually trying to get the computer to understand those patterns without human intervention very often. Right? So patterns are everywhere. So patterns in software engineering, design patterns, are ways of the human brain trained as a software engineer writing lots of code over a lot of time. We'll start to understand that there are these reusable solutions, these things that they see that master coders, really good code, looks like over and over. I know when I did finally get the Design Patterns book after it came out in 94, I think I saw it around 95 or 96. I know when I was reading through it, it really just bowled me over. It's still one of my favorite books that anybody should have, any professional software developer should have on their bookshelf. Because I kept reading and saying, yes, I've seen that before. Yes, that's a great solution. I can understand that higher order vocabulary. So I'm going to walk you through a few examples here. Again, I know you've done a few in previous semester. And I do understand for those of you who maybe have more experience in code, patterns may be something you're already familiar with or something that maybe you'll more readily grasp. Whereas for those of you still relatively new to coding, you're coming up through a curriculum, patterns is a higher order concept that some of these patterns may not immediately present themselves as being obvious in the code. I'll do my best to try and walk through that, but again, over time as you code more, I hope you remember patterns in your daily development life, because as you write more code, as you code review more code, as you get mentored at work or in your professional career, I think patterns will become increasingly important to you. Okay, well, let's get to it. All right, so what's a pattern? There are different templates. Shorter, this is they're all, kind of a short form. This was given in your textbook. A pattern element. So a pattern is a structured, the way it's written is a structured natural language template. So if you actually went to a POP conference, they normally do a tutorial session on the first day that teaches you how to write a pattern according to this template, what the appropriate structure is. This is kind of a short form of the structure. There are longer forms, but here's the basic elements of writing a pattern. First is that you have to have a name for the pattern. That name is, you might say, so what, it's a name, it's just a title. But that name becomes part of the vocabulary. What's going to happen is folks are going to say, oh, you should put an observer here, blah, blah, blah. Right, and that observer name is supposed to make you think of the rest of these pattern elements plus perhaps the code structure, which we'll express in UML after it. What's the problem description? Well, it's the problem, obviously, but the context of the problem too. All right, and you might look at an innocuous description like use when multiple displays of state are needed, but there's some context here around the need for multiple displays of something. All right, and actually, when you instantiate the pattern, you could even elaborate your specific problem a little bit more. The solution description template for a design solution that can be instantiated different ways. Solution description separate for an observer separates the display of the object state from the object itself. All right, that is a natural language description of what we're going to realize in code. And then consequences, the results and trade-offs of applying the pattern. Consequences, optimizations to enhance display performance are impractical, meaning if you're decoupling in this way, you get a good internal design quality element, but a lot of times when you decouple and you separate concerns, as it's called, optimization can be difficult to do. So even when applying the pattern, sometimes, a lot of objects, let me back up a second. The Gang of Four patterns, as it's called, and they're called the Gang of Four because the DesignPatterns book, it was written by four gentlemen, and in fact, I'm going to pause right here, and I'm going to go get the book. Hang on. Okay, I'm back. Where did I go? I ran down to my office because I realized I'm talking about the Gang of Four design patterns, and that's the examples we're going to do. And I figured I might as well go back and go down and get the book and tell you what I mean. You may have seen this book before. I can't actually see the webcam as I'm recording over PowerPoint, so I'm going to hold it right in front of my face. All right, that's the Gang of Four design book, Gang of Four design patterns book. This is a very well-known, very well-established book in software engineering, called Gang of Four because of the four authors that you see there: Ralph Johnson, Richard Helm, Eric Gamma, and John Vlissides. Anyway, very influential book that goes through. And in there, part of the reason I mentioned is you can see in the title, it's Elements of Reusable Object-Oriented Software. So the original patterns and a lot of the pattern stuff has been associated with object-oriented component-based community. That's not necessarily the case. Patterns have been generalized, but it's been associated with the object-oriented community. The original paper that was before this book, the year before this book, actually appeared in the European Conference on Object-Oriented Programming in 1993. I think I'm putting a link to that out on Blackboard. But in any event, I mention that because what happens with a lot of these patterns is it gives you a way to structure your classes and really structure your objects, meaning you're going to instantiate a set of objects that are wired together in particular ways and have particular responsibilities, and they collectively provide a responsibility, a functional responsibility to the larger system. And a lot of times in object-oriented programming, that kind of arrangement introduces more indirection, a little slightly more abstraction. And indirection abstraction is good from our maintainability and our internal quality perspective, but it actually a lot of times can hurt some of our things that we did under dynamic analysis, meaning how fast the code executes, for example. A lot of times the interaction, there's more runtime type identification, more polymorphism, more sequence of calls in your call stack. And that actually slows your code down slightly. All right, computers are very fast nowadays, but still can actually slow your execution down sometimes. And sometimes, it's not very maintainable code, but sometimes something that's really hard-coded, wired together, will actually execute faster because you kind of get rid of all that abstraction and indirection. So in any event, I mentioned that just kind of made me think of that when I was talking about these optimizations here. But in any event, let's move forward and talk about the type of patterns from the Gang of Four. In fact, if you open up the front cover, and again, I don't know how well this will look, but right inside they kind of put a dictionary of what the different pattern types are. Three pattern types: creational patterns, behavioral patterns, and structural patterns. Creational patterns are there to try and decouple clients from knowing how an object is created. Lots of examples in there: it's singleton, abstract, factory, factory method, prototype, and builder, which I'll talk about in these notes. Again, so far in your programming experience, you may just say, well, I need a type of object, so I'll go to the class and just invoke its constructor, right? I'll say, foo x equals new foo whatever, and I'll invoke the constructor, and I'll do it anywhere I want in my application. When you do that, you're introducing some very perhaps inadvertent, innocent coupling, because now the the calling program is tightly coupled to what constructors a specific object has. And very often what happens is you actually start putting on the client, um, or the user of an object, you're asking it to go out and get instantiations of different objects and put them together in meaningful ways. So now the application becomes the integrator, as opposed to the application just worrying about its own application level logic. Right? So creational patterns very often help us with setting up a structure the way it's intended to be used and moving that logic out of the responsibility of the application and moving it back into the framework where it belongs. Again, we'll talk about that with a builder with some examples here in a minute. Behavioral patterns provides guidance on where to implement responsibilities. Behavioral patterns are very interesting. I mean, again, from an object-oriented perspective, um, and hopefully you talked about this some in 315. You'll talk about some more in 415. Um, when you start doing your object-oriented modeling and your object-oriented design of something, before you worry about object-oriented programming, I'm talking about design, you start worrying about modeling your domain. The nature of decomposition and object orientation says you're going to go model your domain objects first. Means even outside an application, you're going to go worry about modeling those things that are part of the business vocabulary of your domain. If you're writing an educational application, it may be the student, the teacher, the classroom, the chalkboard, the textbook, the problems, the notes, the online video lecture, what have you. If it's a stock chart example type of thing, or banking example, which I'm always using in your code examples, right? It's the account, it's the checking account, the savings account, it's the bank, it could be a bank teller, whatever those things that are in that domain. And you model them before you worry about building and wiring them together into a specific application. Behavioral patterns help us kind of understand how to build micro abstractions into our code so that we can extend our system, um, outside of the specific behaviors of the domain objects. So we'll talk about that. We'll talk about observer in detail. That's a common one. Another favorite of mine is a strategy pattern, which basically takes a behavior and abstracts it. We'll talk about, I don't know what we'll talk about, but there's examples of several other behavioral patterns in the Gang of Four book, and it's probably my favorite category because it really enlightens you how you introduce new objects whose responsibility is to help out other objects or to work as those low-level integrators, so you don't wind up building in tight coupling, this hardwiring between specific domain objects. And then the third one is structural patterns, provides guidance on composing objects and classes. And again, we like to reason at coarser grained structures. In fact, in 315 and in here, we've talked a bit about component-oriented computing. Which kind of, we have an object of some kind that produces some interface. Remember your lollipop diagrams for 315, and a component is, basically a simple definition is to call it a bigger object. But in fact, what a component is an arrangement of multiple objects in such a way they provide a larger collective behavior of some kind. And that collective behavior is represented behind an interface. The way that these objects are composed together and the way that they integrate with things outside it, the way that they are extended in different ways, the structural patterns can provide guidance to. So you can create these higher order structures, because the only structure we have really in an object-oriented language, in most object-oriented, I shouldn't say all, but most object-oriented languages, is the class, right? And we want more than, we want arrangements of objects behind a unified interface as part of the structure that we want to reason about in our system. Very often when we are a user of a system, we want to reason about only a few interfaces. When we're an implementer, we've got to reason about a lot more. But we're the implementer. There's a lot more detail behind the curtain, if you will. Okay, so that's a lot of abstract discussion. I know. So let's kind of move forward. and get into some of the examples here in a second. Again, what the design, what the pattern is going to give us is that higher level vocabulary. All right, that's very important. So, for example, you go into a code review and back to a creational pattern. You say, we have to really manage the number of objects we create of a certain kind. Maybe you're creating uh, a number of threads in a system, right? Now you can new up a thread in Java anytime you want, new thread, whatever, right? The issue is if you go around creating too many threads, you increase the chances of deadlock, you increase the chances of race conditions and lost update problems, you increase the chances of dragging down your throughput because too many objects are synchronizing on common things in order to compete for resources. So maybe you want to bound that. So you use a factory to create a thread pool or something like that. You pool that resource and manage all of its instances together. You're managing the life cycle of certain types of objects, right? Because otherwise, if you just new them up, then that object reference you create that you get back from invoking a constructor, now the application is responsible for it. It has to have an explicit awareness of when that thing will be dereferenced and potentially garbage collected. And again, is that what the object application is about? No, not usually. If you could provide a service where you say, give me one of those, give me the appropriate one I need, and you worry about the life cycle for it, when it should be garbage collected and so forth. You've removed the burden from the application programmer. Okay. There's a bunch of other examples of this. We're going to talk about the observer in a second. We'll talk about the decorator, so I'll talk about those here. I mean, again, you saw there's a whole. I don't remember the exact count here of how many of these there are, but and again, the community is even extended to many other kinds of patterns. But there's lots of examples of these. So, for example, the facade is one of my favorite ones. Tidy up the interfaces to a number of related objects that often have been developed incrementally. Basically, the facade is what I just drew in the previous page when I was sitting there drawing this internal one, and collectively, and then they have an interface, and all the client knows about is that interface. That interface could be a facade, right? And again, what does the plain English term of a facade mean? You put up a facade, it's kind of a fake boundary, a fake interface. It hides the complexity. You're putting up a facade behind the complexity of what's actually going on back here because that's not the client's concern. All right. An iterator, maybe you're more familiar with an iterator, a little less complex concept because basically we're just talking about a standard way of accessing the elements in a collection irrespective of how that collection is implemented. So the iterator says, I don't care if you're a linked list of something. I don't care if you're an array of something. I don't care if you're a tree of something. And I don't care even if you're a graph of something. All right, an iterator says I'm going to provide some structured way to walk through each one of these elements because somebody usually wants to visit each element, maybe write a loop to structure their way through them. So they just want to get an iterator that will iterate through the set of elements in that collection. They don't care, a map is another one. They don't care what one it is. You see this all over the Java util collection classes, by the way. Used to be an iterator. The iterators were enumerations, and now they've gone to a more iterator-ish kind of pattern. The enumerations were kind of pre-generics in Java. So let's talk about a few examples. Pulling out one example of each kind of category. So the first one I want to talk about is the builder. The goal of and the builder is actually a reasonably complex one. The goal of the pattern is to produce a complex object. Often the object that's produced by a builder is the facade I just talked about. Or what's called a composite pattern, which I don't have in these notes, a composite pattern. But think of anything that's arranged in an aggregation hierarchy. I didn't even draw that very well. Let me fix that. Let me do this. If you have a composite, what you're talking about is an object like, let's say, a car. And a car is composed of, remember our UML, of many things, right? I have cars in my mind because I just had my car fixed yesterday. It can have an engine. It could have, tires. It can have a body. It can have a doors, I don't know. And then you can talk about parts of the tires, the wheels. So you could talk about the wheel well, and you could talk about the lug nuts, and so on. The engine, you can go into the different parts of it. The doors, you could talk about the handle. All right. And I know I'm making a complete mess of this. The handles, you could talk about these are supposed to be the diamonds from UML. You could talk about the windows. But the point is this is an inheritance hierarchy. This is called a composition hierarchy or an aggregation hierarchy. Well, this is composition because the diamonds are hollowed in. This is part of semantics. Okay. In any event, there are lots of things in the natural world when you're doing your domain object modeling are compositions of things. You can talk about things at a detailed level and the structural level, but then you can refer to them as a whole, right, with all the parts assembled. Now, the point of the builder is the client object. Here in this pattern, in this UML diagram, the director is the thing trying to create something, and it's asking the builder for the different parts of things to try and assemble. If what this is trying to do is avoid making the client, the application, responsible for knowing about this whole structure and how to create each individual part and how to put them together. All right, it doesn't want you to create, I got to have a car with an array of, or a singleton of engines and an array of 4 tires and 1 body and, an array list of 2 or 4 or more doors and so forth. It doesn't want the complex rules and conditions of building something to be embedded over in the application. So instead, it's going to use something that knows how to construct the target. All right, and there can be variations. The concrete builder may have to build variations on things based on the customization for that particular set of objects you're going to do. So, for example, I used to have a Jeep. I love my Jeep, and in my Jeep, do I want to have any kind of car? Right? There's all kinds of packages. Do I want leather seats? Do I want running lights? Do I want a sunroof? Do I want the towing package? It goes on and on, right? Do I want the V4 or the V6 engine or whatnot, right? All these different kinds of options, when you go buy a car, go to Edmunds.com or something like that, and you start picking up all these options. Well, the way to, is something, a particular instance that includes, say, this option and this option, right? That's a parameterized to a build process where now I have to go select which instance of different kinds of objects and configurations will make up this specific car that I'm building. All right, that's the point of the builder pattern. Very often, builders become, larger versions of factory methods or abstract factory. You actually have one of those in your homework. Prototype's another pattern related to a builder. Prototypes, by the way, say start from an example and clone it, basically. But in any event, I'm going to leave this mess on here. Let's take a look at another builder example, what it would actually look like in code. I have an application over here. My app is over here and has a reference to the promo kit director. And it has access to a method that says create promo kit. Now there may be a set of configuration parameters I have to put in here. All right. Might be parameters to that create promo kit, might be in a property file or some other config file like an XML file. But based on the parameterization, the things that basically specify what I want in a promo kit, the promo kit director asks the promo kit builder to build the different parts, right? So here this is a promo kit, so we're building a video part, a garment part, a book part, and a promo kit part. And then here's our subclasses, our specific instances. This is an interface up here. So, if I'm going to build one for men or women, I have gender specific parts of these things. What I'm going to actually create for a video is different for men and women. What I'm going to create for a garment, different, right? Different clothing for men and women, and so forth. All right, um, so that the builder knows how to go and create the specific promo kit that is an This is our hollow diamond. This is aggregation, right? Of different specific garments, videos, and books to put together. All right. So I have different implementations of the promo kit builder so that the app can get back based on a configuration that said, oh, I have Susie, or, I have Bob. All right. And so I get a different arrangement of these things back, but it's completely transparent from the app. All right. Basically, the value here is the app didn't have to go out there and say, oh, if person equals, male or something like that, then give me a new, men's garment and a new men's video and a new men's book. Give them back to me, and I'll start putting them together in different ways. All right. Instead, I get the entire promo kit back. That's the type of thing that gets returned by this method right here. Okay, and the application didn't have to do all this. All right, they just had to make the call with the proper configuration, and the builder built the proper arrangement of these three different objects: video part, garment part, book part. Okay. All right, definitely making a mess of these slides today. Okay, so that's an example of a creational pattern. What about a structural pattern like a decorator? The decorator is, the purpose of the decorator, the problem it solves, is to attach additional responsibilities to an object dynamically. So you decorate an existing object to add those responsibilities. Now, very often this can be done through subclassing, right, to extend functionality. But there may be a few reasons why you don't want to subclass something directly and just make calls to super in it. You may, for example, let me back up for a second and explain. If you're looking at that UML diagram, it may not be obvious to you up front, but this is kind of a strange structure, right? We have some kind of object here called a component, and we have its decorator. The relationship here is subclassing, right? This is our subclass. So in code, we're going to have class component, and then we're going to have class decorator extends component. That's what that would look like, right? It's a subclass. But we also have over here our association link, right? And our association link then says that inside of class D, I'm going to be holding on to some kind of instance of C. So I extend component, yet I'm holding on to a reference to it as well. All right. If I just extended it, then when I had some behavior like execute, right? So in d.execute, if I am just subclassing, I might want to call super.execute. If I wanted to make sure I executed my parent class's instance of the method before I went on and did my own stuff here. All right. But here what we're saying is we actually hold on to an instance of the parent. So my execute may instead, this is on D, might instead call C.execute, because I'm actually holding on to, well, I'm sorry, it's not C, it's going to be my parent, right? C is the class type, and my parent is the instance variable, so I might be calling my parent.execute and then going on and doing my stuff. So it actually keeps, it uses both the subclass mechanism and the composition mechanism in order to provide those additional responsibilities and behaviors. Why would you want to do that? Well, the real reason we want to subclass on something, where did my eraser go? The real reason we want to subclass on something typically is because we want to present the same interface. Right? This class just defines a set of methods like execute. By subclassing, the decorator's got to provide that as well if it wants to provide new behavior. All right? And second is it may say, I want to make sure that I use whatever's here explicitly in its own instance, and all I'm looking to do is to decorate or add some additional behaviors as part of it. Maybe I want to log something. Maybe I want to put up an auxiliary display of something. I'm just trying to provide a new additional incremental responsibility. I want to do it dynamically. A second practical reason is a lot of times you get nervous about directly subclassing and calling super on something if you don't have the source code to it. Very often an instance where I use a decorator is when the component itself is coming out of a third-party library. And I'm a little bit nervous about just calling super on something. Instead, I want to create my own instance and extend the instance here and do things in my own different way, if you will. When you do a decorator, typically the methods that you implement that override the parent class's methods are things that you are decorating or incrementally extending. Right? So decorator is for incremental extension to something. It is not for substitution or replacement. Right? Which means we're still expecting this behavior, whatever's there in the parent class, to be executed, and we're trying to add some new stuff, some incremental new stuff. We're not trying to take this and actually supersede or replace, right? In most object-oriented programming languages, when you subclass and you create something of the with the same method name, you're essentially either replacing a behavior or you're adding to it. The decorator case is only when you are incrementally extending, not when you're substituting or overriding behavior. Okay, so we'll give an example of this. Well, instead of a new example, here's an example that you see all the time. Right, if you're using Java file IO and you look at the different stream types, it's been called the stream zoo in Java. You could see that you normally start with the very low-level interface that talk about reading things in bytes. And then what you do is you wrap. Decorating is often called wrapping, meaning you create a new interface, an extended interface, a wrapper around the low-level implementation so that you can provide new interfaces and extended functionality. So if I want to buffer something, instead of trying to build that as a conditional, I create a new object type that holds on to an input stream internally, but provides the buffering aspect, which means now when I read bytes, I might read them into a buffer first, so I can read ahead and so forth and make higher throughput in my input streaming. I could optimize doing things like reading off a disk for page sizes and so forth. I may have a data stream, reads in bytes and converts to two primitive types. That data stream is used, because maybe we don't want to have the app worry about reasoning at the byte level. It wants to reason in terms of strings or integers or whatever, some higher level or primitive type, and so forth, right? So this is decorating by reusing the underlying implementation that knows how to read at the byte level. It extends that behavior for read bytes in different ways, and then it can also provide its own extended set of behaviors, just like traditional subclassing can do. Right? So we see that, for example, whenever you're creating. That's why when you look, one of the ways you could tell this if you get used to doing Java file IO, which a lot of people don't like, myself included, but you kind of get to this thing where, say, you create a buffered reader, let's say, and in it you've got to give a new, I don't know if I get this right, maybe a new buffered input stream. And the parameter of the new buffered input stream is a new input stream itself, or something like that. And new input stream then might finally take some file name as a constructor. So you get these kind of chained looking constructors going on when you're looking at in Java streaming. And the reason why is because these things are all decorators of something else, so it actually needs the instance to pass into the higher level one to get the last kind of the last one. I guess this is a buffered reader. It would be a new buffered reader with this inside it. All right. Anyway, you get these long chain constructors, and why is that in Java streaming? Because in fact, the Java streams are an example of a decorator pattern, and that's commonly what you'll see. So let's do a third one, and let's do a little bit more of a deep dive. Let's go through all the whole template. And part of this is in your book, and then I've augmented this with some of my own stuff. A behavioral pattern, and this one's common. This one's a good one. I think you might have talked about in 315. I want to talk about in more detail because this is very common in the nature of your project, very GUI driven. Right. So I have a pattern, name of observer, the description of it, and again, this is an expanded version of what was on the initial slide for observer. Description: separate the display of the state of an object from the object itself and allows alternate displays to be provided. When the object state changes, all displays are automatically notified and updated to reflect the change. This is basically, right, we talked about three things an object always has. It has state, behavior, and a unique identifier. The observer worries about changes to this. Anytime there's some change event that comes in for a state, it may say somebody else out here, the observer wants to know. All right, and the observer is going to be responsible for doing something else. It could tell someone else. It could display something new. All right, it could do whatever it wants. You're not going to have to change the original object and add a new behavior to do it because you're moving that behavior out to the observer. Okay. Problem description. In many situations, you have to provide multiple displays of state information, such as graphical display and a tabular display. Not all of these may not be known when the information is specified. All alternative presentations should support interaction, and when the state is changed, all displays must be updated. So again, there may be many of observers at once, is what that implies. This pattern may be used in all situations. So here's some context. May be used in all situations where more than one display format for state information is required, and where it is not necessary for the object that maintains the state information to know about the specific display formats used. So you've done a contacts list that has name and emails of your friends, let's say. The observer can say, oh, I want to render that out to my printer. I want to render that out to a web page. I want to render it for my cell phone. I want to render it for an import to a contacts list app that I have. Why does the contact list object need to know about all those different formats? All right, there's nothing inherent in that domain object where it has to know how it's being rendered. That can be taken care of by having multiple observers. All right. Solution description. This involves two abstract objects, subject and observer, with two concrete objects, concrete subject and concrete object, which we'll talk about in a minute, which inherit the attributes of the related abstract objects. The abstract objects include general operations applicable in all situations. The state to be displayed is maintained in the concrete subject. That's the actual thing being observed, which inherits operations from subject, allowing it to add and remove observers. So in this observer pattern, you actually have to maintain who's watching you, which does require some change on the implementation, and to issue a notification when the state is changed. The concrete observer maintains a copy of the state of concrete subject and implements the update interface of observer that allows these copies to be kept in step. Concrete observer automatically displays the state and reflects changes whenever the state is updated. The ability to say, hey, I want to do a new printout, I want to do a new export to my cell phone, I want to update the web page whenever something actually changed in my context list. Consequences. A subject only knows about the abstract observer and does not know details of the concrete class. Therefore, there's minimal coupling between these objects. That's a good consequence usually. Because of this lack of knowledge, though, that indirection, that abstraction, optimization, that enhanced display performance are impractical. In other words, if there were something that would make it print faster, something that would make it render on your cell phone faster, render on a web page faster, well, the thing being observed, the context list object, doesn't know that it's even being observed and rendered in these different ways, so therefore it's not going to optimize its internal implementation of something. Say, do I use a list, do I use a map, do I use a tree? It's not going to know to do that because it's not even aware. It's decoupled from the ways in which it's going to be rendered. All right. So, what does that mean? So let's say I have this subject object and I have two things watching it. One's responsible for displaying it as a pie chart. The other is responsible for displaying it as a bar chart. What this would basically say is somebody comes along and changes the value of maybe some behavior is done and changes the value of C to 50. All right. So at that point, what this says is C equals 50, and then the subject has to say notify, in concept, notify my observers. This just happened to me. Okay. So how's that happen? Observer 1's told, observer 2's told. Observer 1 here has to go and change the bar chart to give a bigger slice of the pie to C and start taking, little slices away of A, B, and D, since that's a relative display. But the bar chart, has to only change this part of it. Okay. And again, this is a single change to C because this shows absolute values. In other words, when I change C, I didn't have to change A, B, or D. However, maybe over here in the pie chart, I needed to reapportion the chart because this is relative. So I can't really optimize that in subject, how I internally represent these things, because I'm not aware that I'm being displayed relatively over here and absolutely over here. All right. So again, I'd lose the ability to optimize that, which means I am pushing some responsibility into the observer, and there are going to be fundamental limitations on how fast I'd be compared to if the subject actually knew and had its own internal responsibility for rendering both of these displays. That's the trade-off. That's the pros and cons. All right. More deep dive on how you'd actually implement this observer pattern. And this gives you some of the different views that you would look at from an object-oriented perspective. One is, that object-oriented type of diagram. You're going to have a subject. The subject is going to have a register method. The register method is responsible for the observer going to it and saying, I want to register my interest in you. So on the previous diagram, this would be object observer 1 and object observer 2. At some point in their life cycle, would have to register interest in a specific instance of subject. Very often with the register, there'll be an unregister too. Maybe you have a bounded timeline under which you're interested in the other object, so you can register interest in it, and then you could remove interest from it as well. Maybe there's a point in time when, rendering the pie chart is no longer relevant, so observer 1 would unregister interest in it. How the sequence diagram will look, how you would set this up. Normally you have some object that creates your subject and one or more observers, and then tell the observers to go ahead and register. And this register would have as parameters observer and student here. This is actually something you could use that builder for to set up that complex object structure if you want. Then as you're executing after initialization, when the subject has an internal state change, this pound sign here means that this is a non-public method. So internally, when you have something happen that's a state change, then notifications are going to be sent out to the observer. In this case, our state change would be C is now 50 instead of 15. That would trigger that notification call being made. All right. What's in the UML model of this? And again, some of this is this UML diagram is actually straight out of your chapter 7 of your book. Realize that the terminology is a little different than the previous UML diagram. This attach is your register interest. This detach is your unregister that I was just talking about. All right. And basically each observer will be told when there's a state change inside of subject, and when that notify happens, it will call update on each individual observer that it has. Now these are, and this diagram explicitly shows that we have some interfaces. My stereotype on subject is interface, and my stereotype on observer is interface. And so I have subclasses. That's what these are, right? That's our UML for subclass. So the concrete subject would have its own implementation of each one of those methods. The concrete observer would have its own concrete implementation of the update. And perhaps, what it was trying to do was to get the state after the state change. So in this case, C again changed to 50. This is our subject state, included those values for A, B, C, and D. Here, C was 15. Then we updated state. We did something, change it to 50, which means the subject's going to go out and get state. And then for concrete observer 1, that may have been the pie chart. The pie chart will, redraw itself again in different ways. And for concrete observer 2, that may have been the bar chart, and it would change the size of the C to be larger and go all the way up to 50. Okay. Again, that's how that arrangement of objects would realize the observer pattern. All right. And this is a second example of the observer pattern with a little bit of code. This one only shows one observer for something. Here's our interface for the observer. The thing being observed are temperature. So really, this should actually implement some kind of observed interface, which basically gives you the register, right? It tells me I'll take an observer and I'll register interest to me. I'll hang on to them as a list, so I'll just add them to the list. And then when there's a internal state change again of some kind, again, whatever has changed, then I'm going to go out and tell different observers that things that implement the observer interface, and this is using the generic term realizes. For Java, this would have said implements, right? The observer.notify is called, and it would update whatever display it is. In this case, we're talking about a digital display. If it was the HVAC system, it may be something else. That change in temperature may not even be a display thing. Maybe it tells me to kick on the air conditioning or something like that, or kick on the heat or whatnot. All right. So this kind of observing, I mean, realize we could have implemented a class temperature that went out and said, okay, when the temperature changes, I'll go ahead and update the display on my thermostat, and I will kick on the air conditioning, under certain conditions. Or I could decouple that. That feature is over here. The temperature class now only has to worry about changes in the internal state and about basically generating an event, telling everybody about it. All right. In distributed systems and in more scalable systems, the observer pattern is actually generalized into a more generic pattern or architectural style called pub sub, or publish and subscribe, where what the observer is a decoupled object itself, and these folks register to a separate object, so this guy doesn't even have to have a list of observers and is not responsible for doing this kind of loop. That actually happens in the third-party object, and the only thing the temperature needs to know about is, hey, I need to generate an event and tell somebody about it. It's like having an agent, right? It's like me having a TA and saying, hey, TA, I just changed the grading criteria for lab 3. Go tell everybody, right? I tell the TA tells everybody else. All right. That's a very simplified analogy for publish and subscribe. And again, not something that you're required to know from the direct observer pattern. It's what's called a lightweight notification mechanism because there is no intermediate third party there. It is this object itself knows who's observing it and knows to go, provides interfaces to have third-party objects register interest, and will go ahead and notify them of the changes of interest to the object. You'll actually do this on your next lab. And you'll do that because this has been so prevalent. You see it in two common ways inside Java itself. One is the listener. So if you're knee-deep in project code and you're getting used to, perhaps you didn't know and you weren't used to doing event-driven programming with GUI applications, but listeners or observers are used throughout any, not just Java, but pretty much any language for dealing with GUI events. Meaning, when you have something on the screen and then the user here is sitting and moving a mouse or typing something on the keyboard that causes a change in a value over here, right? They're going to point and click a mouse on this, or they're going to go to a text box in the keyboard and type something in. Each one of those actions that they do connected by that device is interpreted as an event, something that can be observed. So if I'm observing a state change to this GUI, either as a whole or even to this individual widget, then I can take some action. I can take some action on every single mouse click, on every single mouse move event, on every single press down and release of a key on my keyboard. There's a tremendous number of things you can actually register or observe in a GUI interface. And then what happens is, you're responsible for writing the code that says what happens, or what do you want to have happen in the application as that's going on. So that listener model, that's why you see, action listener, mouse move listener, mouse click listener, and all these kinds of interfaces all throughout Java Swing. Outside of a GUI, though, it wasn't the original version of Java, but folks realized pretty early on that the observer pattern is not just for GUI applications. It can be done for any generic kind of objects that you want to have, and perhaps you as a domain model or you as an application writer wants to do it as well. So they implemented or provide the APIs that you can find in the Java docs for observable and observer. A class that has really a class that creates object instances that allow themselves to be watched must extend observable. So if you have something that is going to change, like in this case temperature on the previous slide, then temperature would actually, let me clean up here this stuff. Temperature would actually have to extend the built-in java.util.observable, right? Something that actually wanted to watch it, like digital display or HVAC on the previous slide, would have to implement the interface observer, all right, and register their interest. Now, one of the things that observer will provide are things like add an observer to me, all right, which means that this thing would have to provide add observer, and it would have to make sure it can notify observers as well, so it could turn around after these guys add themselves to this guy, it can turn around and tell every time the temperature changed. All right, so it'd be just like the code on the previous slide, except for conforming to these specific Java APIs. It's actually it's an okay implementation, and I say it's okay because one of the things that's bad about it is it actually makes you take a domain object and extend an observable. It's not an interface. You don't implement observable. You actually have to extend the observable class. But it does that because it actually provides the underlying implementation of a data structure to track your observers. Meaning, when you look at examples of observable code, I'm somewhat wary about students going out and looking up their own code snippets for things without understanding them, but there's a lot of examples of observers out there you can find, as well as a standard Java tutorial on it. And I am asking you to do it in the lab. But effectively, because you extend observable, you don't have to have this list right here of observers. You won't maintain that yourself in your own code. The Java is actually providing that for you because this temperature here would extend the observable. All right. Okay. Some wrap up on design patterns. And again, meant to be a review. I know I tend to go on long. Design patterns, and part of the reason we're talking about in this quality construction class is, a pattern is kind of an established arrangement or established low-level way of getting very, very specific contextualized things done in code. And they've been built up over time, this vocabulary, so that, everyone kind of understands that they're useful things to do. How do you use, and that's the part about raising that vocabulary again. If you understand what the observer is, if you understand what the decorator is, the composite, the facade, an adapter, a visitor, a mediator, a prototype, a factory, a singleton, when you understand what these things are and what the implications for your object structure are and what the low-level responsibility is, now when you go into a code review, instead of worrying about where those curly braces are, you can go in and have a conversation with somebody about, hey, over here you should maybe apply a factory pattern or maybe a prototype or maybe a builder to manage the life cycle of the objects you're creating to reduce the burden on the application. Now, you say a sentence like that, If you're not experienced with design patterns, you're going to be like, I don't know what the heck you just said, Dr. Gary. But if you're familiar with the vocabulary and you start to see these things over and over in code, immediately you know what somebody meant by that. All right, and you know what the pros and cons and trade-offs of that. So again, it's that higher order vocabulary level, less effort explaining parts of things, and less effort understanding code of things. Now, for the purposes of this class, and well, not just for this class, but in the context of this class, I want you to think of design patterns in two contexts. One is for new implementations, and the second is for already existing code. For new implementations, it gives you a way to have that design conversation. If you're implementing a new feature for your project, it's a way for you to have a conversation with, let's say, another team partner to say, hey, maybe we should use a factory pattern here to establish a singleton to do X in the system. Again, that one sentence captures a lot of information now because of that higher order vocabulary. In new implementations, we tend to have, well, even for existing code, but realize in object orientation for a long time, we've always had this desire of extending or reusing code in our system by always subclassing something. We always want to subclass and do additional things. Folks actually found that subclassing using extends in a language like Java very often turns out to be a bad thing. And the reason why is the more code exists in the higher levels of a class hierarchy, it's actually harder to reuse it, because one change up here means that all these derivation classes, I mean all the way down the tree, may have to change. Go think of a deep, many levels down inheritance hierarchy, things that may be several subclasses away from an ancestor at the top. You make code changes up here, you actually may have blown something up down here. So object orientation has kind of realized that the best practice for writing object-oriented code is to use is to be more bushy than forest-like, meaning I want small trees or bushes where the top level is an interface, and the implementers are now, this is now realization, so I'll draw it with a dashed line. And the reason why this works is I can use that principle of substitution that we love so much in our object orientation to say, oh, instead of one of these, I want to use one of these instead. Instead of the male promo kit, I want to use the woman promo kit. And I don't have a whole bunch of code dependencies, level dependencies. I only have an interface level dependency to support. All right. So when you do that, you tend to reuse code through delegation and shallow interface inheritance, as opposed to deep implementation inheritance hierarchies. For already existing code, this is where we'll tie into the refactoring we'll do next. Patterns provide I'm still using my eraser. Patterns define a target for refactoring. So when you're looking at a low-level mess of code, somebody's not managing the life cycle of objects well, somebody is not has a big bloated class with a whole bunch of stuff coupled into it, you may look at a refactoring and say, I can introduce the creational pattern, or I can introduce the factory, I can introduce a builder, I can introduce a prototype. You may look at that big jumbled class and say, oh, I can introduce an observer and decouple and move away from that class. All these things that don't seem at the core of its existence, and things that I can move out and make that class smaller and make its responsibility obvious, if you will. All right. So that's what we want to do with design patterns. The target, this is going to go hand in hand with the refactoring that we do next. I'm going to ask that you look for opportunities, in particular with already existing code, to introduce some better patterns in your project level code. There's a lot of readings, there's a lot of stuff out there on patterns. There's still folks doing advanced research on it today, but now it's really in every software developer's toolkit. Again, I got my books here. This is a book for every software developer's bookshelf. I recommend that every student buy one. There's additional ones. There's actually a whole discipline on arranging. We've been talking at the level code level. When you're talking about big coarse components of a system or services and how they get arranged and composed, there was a book also in the mid-90s from the software architecture perspective. Kind of suggests that a much higher level, that you start looking at software architecture patterns. Patterns at the architecture level are referred to architecture styles, and Shaw and Garland wrote this book. Hopefully, that's coming through. And in this book, it talks about. I don't think it has it on its. And there's a. These folks were at the Software Engineering Institute at Carnegie Mellon. And there's a technical report, so you can even get the tech report. You don't have to buy the book. This is another book on the bookshelf. You can't really see the table of contents, but when you get to chapter 2, it talks about different. I'm sure you're not going to see this, but it talks about different architecture styles, like a blackboard style, a pipe and filter, a micro kernel, implicit invocation, and things like that. So there's a category of larger things that you talk about. There's a lot of patterns, but Glenda Rising, a native of Phoenix and a graduate of ASU actually out here, ran a number of the PLOP conferences. She was very involved in the patterns community for a long time. She's still around. Came out with the Patterns Handbook. I think there's a second one that she did. And again, these are, as all of these as these pattern writing workshops came around, she basically was collecting them all. So this book is full of all additional patterns, whether in code, in process, or whatnot. And then next we'll talk about patterns, as I said, but there's a whole book even on refactoring and targeting patterns associated with things. So again, that goal of taking existing code and trying to improve its code quality in place, which is what we're going to talk about next with refactoring.